All right, so let's move on to our third presentation. The presenter of the third presentation is Haiyun. She is a fourth-year PhD student in computer science in Hong Kong University of Science and Technology. Her research interests include optical sensing, smart healthcare, and artificial intelligence of things. And today she's going to present BabyNutri, a cost-effective baby food macronutrients analyzer based on spectral reconstruction.
Thanks. So good afternoon, everyone. I'm Haiyun, a fourth-year PhD student from the Hong Kong University of Science and Technology. I'm very glad to be here to introduce our work, BabyNutri. So why baby's nutrition intake is important? According to the reports, the nutrition early in life is essential to ensure baby's growth, health, and development to their full potential. And especially the micronutrients, or the carbohydrate, protein, and fats, play long-term effects on baby's growth of muscles, bones, and neural development. So mothers may want to know whether the food consumed by their children is up to the specified nutrition intake recommendation. But currently, the most common way to record the baby's nutrition intake is by hand logging, which could be too cumbersome to be sustainable. In addition, there are some camera-based solutions that gain great success in food nutrition detection, but different with normal food. The baby food always mix all ingredients together and meal to paste, so there is no enough visual features to support the computer vision technology. And in this case, the spectroscopy technology can obtain better performance by detecting the deep chemical characteristics of the food. And more specifically, the spectroscopy can reflect the chemical bonds in the food sample. And since different nutrient contains different chemical characteristics, each nutrient will have a distinctive near-infrared absorption spectrum. But a professional spectrometer is very expensive, which costs more than hundreds of dollars, hindering its accessibility in daily lives. And to reduce its cost, in recent years, some research efforts have tried to propose low-cost optical signal-based solutions. Their basic idea is to leverage cheap LED and photodiode components to construct a cost-effective spectroscopy system, which is less than $50. But this kind of design greatly sacrifices the spectral resolution, which can only obtain a coarse-grained low-dimensional spectral. So as we can say, comparing with the high-dimensional one that collected by the professional spectrometer, a lot of spectral features are missing. So it's hard to obtain accurate macronutrient estimation by these kind of systems. And here we ask the question, can we propose a low-cost spectroscopy system without sacrificing the spectral resolution to enable accurate baby food nutrition detection? The answer is yes. Our idea is to combine the low-cost hardware with spectral reconstruction algorithms. And in specific, we first obtain a low-dimensional spectral by cheap hardware, and then apply reconstruction algorithm to reconstruct the high-dimensional spectrum. So you may ask the question, why? Why can we conduct such a spectral reconstruction process? To understand the why, we need to look at how the spectrometer works. Actually, both the professional one and the low-cost spectrometer obtain the spectrum contains 3 parts: the light source E, and the food sample reflectance F, and the hardware parameters S. So the main difference here is the hardware parameters, or the response curves. And for a professional spectrometer, it may contain hundreds of sharp response curves. So it can generate a high-dimensional spectrum with hundreds of points. But for a low-cost one, it only contains several broad response curves. So it only generates a low-dimensional spectrum. But even the different grain size of the response capability, we can say that both systems covers the same wavelength band. Or we can say that they can detect the same optical information of the food. So in other words, each point in a low-dimensional spectral contains equal information with a wide band in high-dimensional spectral. And the principle of spectral reconstruction is to learn the mapping between the hardware parameters of the two systems. So based on this idea, we propose BabyNutri. It's a low-cost baby food macronutrient analyzer based on spectral reconstruction. The system obtains the nutrient estimation in 3 steps. Firstly, we design a low-cost photodiode array-based spectrometer, which can obtain a 5-dimensional spectrum of the food sample. And then, the low-dimensional spectral will pass through a spectral reconstruction algorithm and transfer into a high-dimensional spectral, which contains 160 points. And finally, the reconstructed spectral will be used for nutrient estimation by a convolutional neural network-based deep learning model. So you can see more details about the hardware design and the algorithm design in our paper. And here, I want to illustrate more about our spectral reconstruction algorithm. Actually, to eliminate various environmental influence, such as ambient light and surrounding scatterings, we designed such a 2-step denoise autoencoder spectral reconstruction model. The first step, we use a linear regression to obtain a roughly reconstruction output. And then we take the output in the first step as a noised high-dimensional spectrum and feed it into a denoise autoencoder. So the objective of the denoise autoencoder model is to minimize the error between the reconstruction one with the ground truth. And meanwhile, it should keep the shape of the 2 spectral as similar as possible to support later nutrient estimation. And we design and implement a compact and low-cost prototype using off-the-shelf components. The system costs less than $10 except for the control unit. And we evaluate the performance of BabyNutri on 88 different types of baby food. So here is the overall performance. We can find that BabyNutri's performance is highly correlated with the professional spectrometer, with the correlation coefficient more than 0.8 for all 3 nutrients. Well, the price of our system is only 1% of the commercial spectrometer. And we also tested the spectral reconstruction performance on other food types like juice, coffee, and milk. The reconstruction error is less than 2%, showing good generalizability of our algorithm. And here, we should note that one shortcoming of BabyNutri is that it's limited to evenly distributed food samples. But this is enough to use as most of the baby food are evenly distributed. Another thing you need to note is that BabyNutri is promising to extend to other applications by easily replace with different spectral analysis models, such as food adulteration identification or liquid quality detection. So in conclusion, we propose BabyNutri, which is a low-cost system but can achieve comparable performance with commercial solutions for baby food macronutrient detection. And we hope our work can inspire more interest on near-infrared spectroscopy technology in ubiquitous applications. That's all about my sharing. Thanks for listening.
Okay. We can have 1 or 2 quick questions. And in the meantime, the 4th speaker, would you please come with your laptop and then set up?
Really cool. Thank you so much for that presentation. So with hyperspectral cameras, I'm interested in knowing, are you better at classifying between different foods and then distinguishing between levels of carb, fat, and protein? Or is it sort of you classify first the food and then you're able to use this to distinguish between the different levels of macronutrients?
Actually, we didn't do the classification. We do the regression to different nutrition levels.
Got it. So you know the food type, and then you use the hyperspectral image to then be able to reconstruct, to be able to distinguish between macronutrient level.
Oh no, we didn't. We didn't know the food type, and we actually we didn't consider the hyperspectral image. We just consider the spectral, the
Oh, I see.
one-dimensional spectral. It's a kind of signature of the food sample.
Got it.
So by
Got it.
identify such a signature of the food sample, we can know what's nutrient level in that food sample.
Got it. Thank you.
Can you make it quick? Can you make it quick?
Okay, and thank you. Very interesting work. So I just want to ask you, how do you control your sample? For example, if different food, actually the temperature could be different, and also how you also control the amount of your sample when you measuring the result? Okay, thank you.
Okay, thanks for your question. Actually, we try different amount of the food sample and also the different temperatures in our paper. So you may find more details in our paper. And I can briefly tell you the result that if our system work in very low temperature, the performance is maybe a little bit not good. But other cases, it can work very smoothly.
Okay, thank you.
Okay,
Thank you. Thank you. All right, let's move on. So our fourth speaker is Huang. He is a third-year master's student in computer science in Nanjing University. His research interest includes human-computer interaction, wireless sensing, and